Welcome back to Module 1, Unit 2, Lesson 5 of our study of the fundamentals of operating systems, based on the text Operating System Concepts, 10th edition, by Abraham Silberschatz, Greg Gagne, and Peter Galvin, published by Wiley Publishing. Make sure you have your study guide ready, and let's pick up where we left off. Another aspect of a modern system is its collection of system services. Do you remember our diagram of the logical computer hierarchy? At the lowest level is the hardware. Next up is the operating system. Then the system services, and finally application programs. System services, also known as system utilities, provide a convenient environment for program development and execution. Some of them are simply user interfaces to system calls. Others are quite a bit more complex. They can be divided into these categories. File management represents programs that create, delete, copy, rename, print, list, and generally access and manipulate files and directories. Status information. These are programs that simply ask the system for a date, time, amount of available memory, or disk space, number of users, or similar status information. Others are more complex, providing a detailed performance, logging, and debugging information. Typically, these programs format and print the output to the terminal, or some other output device, or files, or displays it in a window of the GUI. Some systems also support a registry, which is used to store and retrieve configuration information. Next category is file modification, which refers to several text editors that may be available to create and modify the content of files stored on the disk or other storage devices. There may also be special commands to search contents of files or perform transformations of text. Another category is programming language support, which involves compilers and assemblers and debuggers and interpreters for common programming languages such as C or C++, Java, and Python. These are often provided with the operating system or available as a separate download. Another category is program loading and execution. Once a program is assembled or compiled, it must be loaded into memory to be executed. The system may provide absolute loaders or relocatable loaders, linkage editors, and overlay loaders. Debugging systems for either higher level languages or machine language are needed as well. The fifth category is communication. These involves programs that provide the mechanism for creating virtual connections among processes, users, and computer systems. They allow users to send messages to one another's screens, to browse web pages, to send email messages, to log in remotely, or to transfer files from one machine to another. That's communication. Another category is background services, which are general purpose systems that have methods for launching certain system program processes at boot time. Some of these processes terminate after completing their task, while others continue to run until the system is halted. Constantly running system program processes are known as services, subsystems, or daemons. One example is the network daemon we talked about earlier. In that example, a system needed a service to listen for network connections to connect those requests to correct processes. Other examples include process schedulers that start processes according to a specified schedule, system error monitoring services, and print servers. Typical systems have dozens of daemons. In addition, operating systems that run important activities in user context rather than in kernel context may use daemons to run these activities. And the last category, of course, are application programs. Along with system programs, most operating systems are supplied with programs that are useful in solving common problems or performing common operations. Such applications include web browsers and word processors, text formatters, spreadsheets, databases, and so on. The view of the operating system, seen by most users, is defined by the application and system programs rather than the actual system calls. Consider a user's PC. When a user's computer is running Windows operating system, the users might see the GUI featuring a mouse and Windows interface. Alternatively, or even in one of the windows, the user might have a command line shell, like we did earlier in this lesson. Both use the same set of system calls, but the system calls look different and act different in different ways. Further confusing the user view, consider the user dual booting from Mac OS into Windows. Now the same user on the same hardware has two entirely different interfaces and two sets of applications using the same physical resources. So on the same hardware, a user can be exposed to multiple user interfaces sequentially and concurrently. A system as large and complex as a modern operating system must be engineered carefully to function properly and be modified easily. A common approach is to partition the task into smaller components or modules rather than have one big system. Do you remember the concept of modular programming from your programming class? Each of these modules should be a well-defined portion of the system with carefully defined interfaces and functions. You may use a similar approach when you structure your programs. Rather than placing all of your code in the main function, you separate logic into a number of functions, clearly articulate parameters and return values, and then call those functions from the main. We briefly discussed the common components of the operating system in the first unit. In this section, we discuss how these components are interconnected and melded into the kernel. The original MS-DOS was written to provide the most functionality in the least space. Actually, the original MS-DOS or PC-DOS was purchased by Microsoft from the Seattle Computer Company, just so Microsoft could satisfy requests from IBM for an operating system for their new IBM PC. It looked very little like the Windows in use today. That original operating system was meant from the get-go to be simple and easy to run on one of those early PCs. The simplest structure for organizing an operating system is no structure at all. That is, place all functionality of the kernel into a single static binary file that runs in a single address space. This approach is known as the monolithic structure and is a common technique for designing operating systems. An example of such limited structuring is the original Unix operating system, which consists of two separate parts, the kernel and the system programs. The kernel is further separated into a series of interfaces and device drivers, which have been added and expanded over the years as Unix has evolved. We can now view the traditional Unix operating system as being layered to some extent, as shown in this figure. Everything below the system call interface and above the physical hardware is the kernel. The kernel provides the file system, CPU scheduling, memory management, and other operating system functions through system calls. That is a lot of functionality combined into one single address space. The Linux operating system is based on Unix and is similarly structured. The Linux kernel is monolithic in that it runs entirely in kernel mode in a single address space, but as we'll see later, it does have a modular design that allows the kernel to be modified during runtime. Despite the apparent simplicity of monolithic kernels, they are difficult to implement and extend. Monolithic kernels do have a distinct performance advantage because there is very little overhead in the system call interface, and communication within the kernel is fast. Therefore, despite the drawbacks of monolithic kernels, their speed and their efficiency are why we still see evidence of this structure in Unix, Linux, and Windows operating systems. The monolithic approach is often known as a tightly coupled system because changes in one part of the system can have wide-ranging effects on other parts. Alternatively, we could design a loosely coupled system, such as a system divided into separate, smaller components that have specific and limited functionality. All these components together comprise the kernel. The advantage of this modular approach is that changes in one component only affect that component and no others, allowing system implementers more freedom in creating and changing the inner workings of the system. A system can be modular in many ways. One method is a layered approach, in which the operating system is broken into several layers or levels. The bottom layer, layer 0, is the hardware. The highest layer, layer N, is the user interface. This layer of structure is depicted in this figure. An operating system layer is an implementation of an abstract model made up of data and the operation that can manipulate those data. A typical operating system layer, let's say layer M, consists of data structures and a set of functions that can be invoked by higher level layers. Layer M in turn can invoke operations on lower level layers. The main advantage of the layered approach is simplicity of construction and debugging. The layers are selected so that each uses functions or operations and services of only lower level layers. This similar approach simplifies debugging and system verification. The first layer can be debugged without any concern for the rest of the system because, by definition, it uses only the basic hardware, which is assumed correct, to implement its functions. Once the first layer is debugged, its correct functioning can be assumed while the second layer is debugged, and so on. If an error is found during the debugging of a layer, the error must be on that layer because the layers below have already been debugged. Therefore, the design and implementation of the system are simplified. All of this should remind you of the modular approach from your early programming classes. Each layer is implemented only with operations provided by the lower level layers. A layer does not need to know how these operations are implemented. It needs only to know what these operations do. If you've taken my Networks and Distributed Systems course, all of this should sound familiar because that is exactly how layers and data communication work. So, each layer hides the existence of certain data structures, operations, and hardware from the higher level layers. Layered segments have been successfully used in computer networks like TCP and web applications. Nevertheless, very few operating systems use a pure layered approach. One reason involves the challenges of appropriately defining the functionality of each layer. In addition, the overall performance of such systems is poor due to the overhead of requiring a user program to traverse through multiple layers to obtain an operating system service. Some layering is common in contemporary operating systems, however. Generally, these systems have fewer layers with more functionality, providing most of the advantages of modularized code while avoiding the problems of layer definition and interaction. Okay, let's take a break right here. I want you to go back and study your notes. Make sure you have a clear understanding of the kinds of services that the operating system provides through use of the system utilities, and also begin to get a grasp on the concept of the monolithic operating system, one big system in a single address space. Also, after taking your programming courses, you really should appreciate the concept of modularity, by separating a very complex object like an operating system or other very complex software that perhaps you've even written into separate modules that are all self-contained, that interact with one another, so that you are able to isolate the functions that they perform, and as a result be able to isolate your debugging tasks that you have to do. That is a very significant approach to system design.